Okay, so I am Aurel Page, and I will lecture on computational mathematics with a focus on number theory. And this lecture will be mostly about algebraic number theory. Okay, so welcome to the second lecture. I will quickly give you a reminder of the first lecture. So we talked a little bit about complexity. So what is complexity? It's the running time of an algorithm expressed as a function of the size of input, or sometimes with variance. And I gave you 4 broad complexity classes just to have a quick idea of what size you can reach with a certain algorithm. So fast algorithms, quasi-linear, medium, polynomial but not quasi-linear, slow, sub-exponential, and very slow exponential algorithms. And well, I didn't give a name to even worse. Okay, then we talked about arithmetic operations. So a quick summary. Basically, all the basic operations on integers and polynomials are fast. The basic operations on matrices are just medium, polynomial time, but not quasi-linear. Factorization of polynomials can also be performed in polynomial time, so medium. And factorization of integers, that is harder, this is slow. Okay? So the plan for today's lecture, so I will do a little first section before algebraic number theory about algorithms using reconstruction. And this is sort of closely related to the first lecture, but didn't quite fit in it. So I will describe them because that's a useful kind of technique to have in your toolkit. And then I will describe a lot of algorithms, give a broad overview of all the important algorithms in algebraic number theory. Okay, so reconstruction. So what is reconstruction? So reconstruction is a way that you can recover a certain object. So typically a number or polynomial, but it can also be something that is made of numbers and polynomials, from specializations or approximations. So let me give you the most basic example. So reconstruction of an integer can be either real reconstruction, if you have a real approximation to 1/2 of the integer, then you can round it and you get the integer back. Okay, so you can compute integers from their approximations to sufficient precision. And you have the corresponding version for modular arithmetic. So if you know your integer modulo some d, and d is large enough compared to the size of the integer, then you can recover the integer by doing a centered lift. So you have to lift between minus d over 2 and d over 2 instead of 0d, just because they are negative integers and you wouldn't recover them otherwise. So I will describe a few more reconstruction techniques, but first I want to explain why this can be useful in general. Well, there's 2 main reasons. One is that it allows you to control the size of objects during a computation. If you do computation, for instance, with real numbers, with bounded precision, these objects don't grow too much. You can control better how much they grow. And if you know in advance the size of the output, then you can do reconstruction at the end. And same thing for arithmetic modulo some integer. This allows you to bound the size of everything that happens during the computation and recover the result at the end. So that can be one reason. And the second one could be just because you have better tools in the specialized or approximate version. For instance, if you do real reconstruction, that could be because you have access to analytic functions and things like this, even if you want to recover a real result, an integer result at the end. So just a simple example of an application. If we take d, an integer, we can define the cyclotomic polynomial, phi d. This is just the products of x minus zeta, where zeta ranges over primitive d-th roots of unity. And we know that this polynomial has integer coefficients. In fact, we can also give reasonable bounds on the size of the coefficients. And to compute that polynomial, even though it's integral, one easy way to do it is to actually use the complex roots of unity, compute this product as a complex polynomial, and then recover the integers. Okay, so that's sort of the prototype reconstruction algorithms, and there are many interesting polynomials, in fact, in number theory that you compute this way, like modular polynomials or Hilbert polynomials, and etc. Okay, so I want to give you a few more reconstruction techniques. So the first one is simply, well, we talked about reconstructing integers from the integer modulo n, but very often it's actually even more convenient not to work modulo n, but modulo several integers that are even smaller. And so why can you do that? Well, if you choose pairwise coprime integers, you know that z mod nz is isomorphic to the product of the z mod ni z, just by reducing modulo the ni. And so the direct map is the easy one. You just reduce modulo the small primes. And the inverse map is the reconstruction one. And this can be performed with a fast algorithm, so really quasi-linear. So it's very efficient. Okay, there is the version for polynomials, which is interpolation. So you choose a set of points that will be your interpolation points for your polynomials, and then you want to interpolate polynomials of bounded degree. And you know, well, that the evaluation map is an isomorphism of vector spaces. Actually, even preserves the multiplication as long as the degree is not too large. And so the inverse map is the reconstruction one. This is the interpolation map. And again, you have really fast algorithms, quasi-linear. So if you remember, actually, we used something like this in the first lecture when we studied fast polynomial multiplication using the fast Fourier transform. We were evaluating at roots of unity and then reconstructing the polynomial at the end by interpolating. And I explained how you could do that quickly using the special properties of roots of unity. Here, this is for arbitrary evaluation points, but you cannot actually use that to design a fast multiplication algorithm. That would be circular because this uses fast multiplication. Okay, so you need to do it first for roots of unity to have fast multiplication, and then on top of that you can build this. Okay, then a bit more interesting, rational number reconstruction. So if you are looking for a rational number and you want to reconstruct it from real approximations, there can be two situations. Sometimes you actually know a bound on the denominator, like a valid denominator, a multiplicative bound on the denominator, and then you can just reduce to integer reconstruction. There's not much to do. Sometimes you don't know an actual denominator, you just know a bound on it. So like a bound on the height of the rational. And in this case, you can use continued fractions on the real numbers to reconstruct it. So just a quick overview of what is continued fractions. So you have a real number, and well, let's say that it's actually not a rational. So you just write R is its integer part plus something, or maybe the closest integer. And the something will be between 0 and 1. So you invert it, and then you get something bigger than 1. So you can then put another integer here, just do the same process again. And then here you'll get something less than 1, etc. And the theorem tells you that every good rational approximation of a real number appear as one of the fractions that appear if you stop somewhere in this expansion. Okay. And all of this can be done quickly, so that's a way of reconstructing rational numbers. And again, there is the rational functions version, the polynomial version. So in this case, we will use approximations by, well, power series, which just means like a truncated polynomial, like the power series expansion at 0 or another point. And in this case, you know that it's possible to reconstruct a rational fraction as long as the number of terms that you have is bigger than the sum of the degrees of numerator and denominator. This is what you expect in terms of number of coefficients. And this is called Padé approximants. And there are also quasi-linear algorithms to compute these Padé approximants. So this is also a reconstruction that you can do quickly. Okay, and the final type of reconstruction I want to mention is Chronicle substitution. So it works like this. So for, say, polynomials with integer coefficients, if you know a bound on the size of the coefficients, you can evaluate the polynomial at a large enough integer, call it b here, and the polynomial can be recovered completely just from this evaluation. If you think about simply you take your, well, let's say for simplicity that the pi's are between 0 and b minus 1, that would be slightly simpler, then these pi's are just the digits in the base b expansion of this integer. So you recover the coefficients like this. So this way you can reduce some operations on polynomials to operations on integers. So actually, I think originally this was invented well, by Chronicle, and he was using it to factor polynomials. So he was factoring polynomials by evaluating them at integers and factoring the integers. And actually, if you remember the complexity of factorization of integers and polynomials, this is a terrible idea. Because polynomials you can factor in polynomial time, whereas integers you can't. I mean, we don't know how to do it. So it's not used for that anymore, but it's very useful in other contexts. And you can also do this if you have several polynomial variables. You can reduce to one less variable by a Chronicle substitution. You simply specialize one of the variables to x to some exponent that is larger than the degree of the coefficient when you expand in terms of that variable. And then in the same way, you can recover the multivariate polynomial from the one less variable polynomial. So this is a way of reducing, well, some operations, even just very basic ones, to fewer variables in your polynomial. Okay, so this was for the reconstruction algorithms. A few of them will appear in the algorithms that we'll see. So now I will make a broad overview of algebraic number theory and the corresponding algorithms. So maybe to start with, so we're going to talk about number fields, but maybe some of you actually like better to think geometrically in terms of function fields. So I just want to give a quick analogy if you find that more convenient, just well, if you're more used to thinking about function fields and curves than number fields. So the analog of a number field is a function field of a, well, smooth projective curve over a finite field f. And one thing you need to be slightly careful about is that there isn't a single copy of the rational function field inside of f of c. So to have a correct analogy, you need to choose a morphism to P1. And that will give you the analogy, the analogous thing as Q inside of your number field. Then the analog of the ring of integers will be the ring of regular functions away from the points above infinity. Then the analog of an ideal will be a divisor. Well, strictly speaking, I should ask that it's not supported at the infinite points. And then the class group will be analogous essentially to the Jacobian, really to make a very precise analogy, you'd need to tweak the Jacobian a bit, but in terms of just having an analogy in mind, that would be sufficient. Okay, so since we are going to talk about the complexity of various algorithms, we need to pin down what the relevant parameters are going to be. And for number theoretic algorithms, the size of input itself is usually not really the best parameter. It's a bit too coarse. So the most significant parameters are going to be the degree of the number field. So a number field has finite degree over Q. I'm going to denote that by D in the lecture. And that's usually a relevant parameter. And the discriminant of the number field is also usually a good one. It's a measure of the, of the complexity in a mathematical way of the number field. Sometimes it's even more complicated. I mean, the behavior of some algorithms is not completely clear, and there can be more things that play a role. So we will not always have a very clean complexity statement, but we will do it when we can. Another comment about these two parameters, you can actually prove that the degree is bounded by some constant times the log of the discriminant. So in principle, you could forget about the degree and bound everything in terms of the discriminant, but that would be a bit coarser, so it's usually better to keep the two parameters. And yeah, and this is optimal in the sense that there are also sequences of number fields of growing degree whose discriminant grows just exponentially in the degree. So this is the best you can get. Okay, so here are the main problems of computational algebraic number theory that we are going to talk about. Given a number field, you want to compute the ring of integers, you want to compute the Galois group of the Galway closure of the field, you want to compute the class group, and you want to compute the union group. We will also talk a little bit about other operations, like some basic operations with elements and ideals, because that's also going to play a role. But these are the biggest problems. Okay, so first a few operations about number fields. So we can always choose a single element that generates the number field over Q. That's called the primitive element theorem. And so every number field can be represented as polynomials modulo P, where P is monic irreducible, and we will take it to have integer coefficients that will be convenient, and of degree, which is the degree of the number field. So every number field can be written this way, and if you choose a P like this, this is a number field. Okay, so I'll call this P a defining polynomial everywhere. And there are many defining polynomials for the same number field, but there's always one that is not too large in terms of the degree and the discriminant. That's sort of why the size of the input is not so relevant. You can actually bound it if you change your defining polynomial in terms of degree and discriminant. Okay, so first I want to describe comparisons of number fields that you can do. So the first problem you would like to ask is, if you have two number fields, can you test whether they are isomorphic, or maybe even more precisely, if one embeds in the other? And so first I want to recall a few basic properties. If you have a ring homomorphism between number fields, then it's always an embedding. In fact, this is true for any fields. And because they both have a finite degree, this embedding will be an isomorphism if and only if the degree is the same, just by dimension comparison. And so we are simply reduced to finding homomorphisms, ring homomorphisms between number fields. And because we represent our number fields in this way, well, a ring homomorphism is just given by take x to some value in k, but it should satisfy this relation. It should be a root of p. So the homomorphisms to any other field are exactly given by, we map alpha to beta, where beta is some root of p. And in particular, we are simply reduced to the problem of finding roots of polynomials over number fields. And as we said, this is something we can do in polynomial time. So this is a medium speed algorithm. So that rules, yeah, that gives you embeddings and in particular isomorphisms between number fields. Okay, then another operation that you may want to do is you have a first number field and you want to extend it to a bigger one instead of just constructing them directly from Q. So if you have your number field f and you have another polynomial now with coefficients in f, you would like to extend f by adjoining a root of this new polynomial, well, assuming it's monic and irreducible again. And so, well, if you just look at it like this, you get a representation that's not of the type that we took before. That would be q, x, y, modulo p and q, so modulo two variable polynomials. So we want to reduce it to the primitive element form that we had before. And that's actually relatively easy to do. There always exists an integer, in fact, a small integer, such that k is generated by the element beta, the root of the new polynomial, plus a smaller multiple of alpha, the generator of the base field. And you can find a defining polynomial for this very quickly using resultants. Remember, we discussed resultants as a tool to manipulate numbers represented by their minimal polynomial, by a polynomial which has them as a root. And so here we can simply take the resultant of p and q of y minus k times x, and if you work out what happens here in terms of the root of p, this will give you exactly this. So it's actually fast to find this new defining polynomial. Now that we have ways of comparing and constructing number fields, we can start working with elements in there. So just by our representation, any element of f is uniquely represented by a polynomial in qx of degree less than d, and you can find this unique representative by division with remainder modulo the defining polynomial. So all arithmetic operations just reduce to those for polynomials, so it's all polynomial time. Just one word of warning, in practice division is not such a nice operation. You have a lot of coefficient growth when you divide algebraic numbers. So in fact, there are algorithms where you can very quickly find the output, which is supposed to be an algebraic number, in the form of a ratio of two algebraic numbers. And if you force yourself to give the output in this form, you have to divide, and this is actually the bottleneck of the whole algorithm. So that's something to keep in mind sometimes. Okay, one extra basic operation on elements, that's trace and norm in number fields. So if you take lambda, an element of f, which I will represent by a polynomial in alpha, and we'll think about the multiplication by lambda map on f, then this allows us to define the trace and the norm of lambda by taking trace and determinant of this endomorphism. Okay, so the trace is quite easy to compute because it's linear, so you could even pre-compute it on a basis, and then you just have to do the linear combination of the values on the basis, so this is not so interesting. The norm, if you simply apply the definition, it tells you to take the determinant of this endomorphism, for which you could compute a matrix and compute the determinant, but that's not actually such a good idea because, well, this is polynomial time, but it's not quasi-linear, it's not so fast. Instead, it's much better to use the fact that the determinant is also the product of the eigenvalues, which in this case is going to reformulate into the norm is just the resultant of P, the defining polynomial, and R, the polynomial representing your element. So this is an instance of what I was saying a bit, well, I think in the first lecture, then sometimes you have two options to represent objects, either by matrices or polynomials, and it's, well, if you have these two options, it's always better to choose the polynomial things because you'll have access to fast algorithms. That's the norm example, is a good example of that. Okay, I think we can take a short break here. Are there questions? Okay, so now I will describe the first important task of algebraic number theory that I was mentioning, which is computing the ring of integers. So the computation of rings of integers using the notion of orders. So what's an order in F? It's a subring that is generated over Z by a basis of F. So think of O, which is Z alpha. So polynomials in alpha, but only with integer coefficients. This has a basis, which is 1 alpha, alpha squared, up to alpha to the d minus 1. So it is indeed generated over Z by a basis of F. And it is a subring because it's just polynomials in alpha. Okay? So that's the basic example of an order. And the ring of integers itself is also an order. That's one of the basic results of algebraic number theory. And every order is contained in there because, well, you can see from those properties that every element of an order have to be algebraic integers. And so, reformulated, this means that the ring of integers, it's the largest order among all. It's the maximal order. So the way we are going to want to compute the ring of integers is you start with an order, usually this one, and then you try to increase it until you reach the maximal one. And so a useful notion for that is the notion of discriminant of an order, and that's simply the determinant of the trace the determinant of the trace bilinear form. So determinant of this trace of pairwise products of elements of the basis. That's always an integer and it's non-zero. And a few useful properties. Well, okay. So the discriminant of F by definition is the discriminant of the ring of integers. If you have a containment between two orders, they will have finite index because they're both generated by over Z by a basis of the field, and so you have a relation. I mean, they have a finite index, and the discriminants are related just by the square of the index. And finally, well, here we have another example of a computation that we should do with polynomials instead of matrices. If you look at this definition, you're supposed to compute the discriminant using the determinant of a matrix. But in fact, for Z alpha, this determinant is also a resultant. And so you can compute it quickly. So that's a better way to compute this, this discriminant. P is the defining polynomial of the field, so it's the minimal polynomial of alpha. So yeah, to compute the ring of integers, we start with a certain order, usually Z alpha, and we increase it until we can't anymore. So we are reduced to the question of how do we know that we can increase it or not? How do we increase it if we can? So for this, I will introduce a useful notion, not just in this context, but more generally in groups, in abelian groups. It's a notion of saturation. So I'll fix P a prime. I'll give you the saturation in the two notations, multiplicative and additive. So let's think of G is an abelian group here in multiplicative notation, and we have a subgroup H. By definition, the P saturation of H inside of G, it's the set of all elements of G that have a p power that is inside of H. So the way you should think about it, you take elements of H, you extract p fruits as long as you land in G until you can't anymore. Okay, that's p saturation. Another way to express exactly the same thing is to say that the p saturation is the smallest subgroup between H and G, such that the index here at the end is not divisible by p. If the index was divisible by p, that would mean that you can extract a p fruit again here. So in additive notation, because for others that's what's actually going to appear, in this case it's the set of elements of the big group, such that some p power multiple is inside of B. So in other words, you take elements of B and you divide them by powers of p as long as the result lands in A. So there's a basic algorithm, but very slow, that computes the p saturation, which is simply you try every element of B modulo p, and for each of them you try to either extract a pth root or divide by p, depending on your context, and you try to see if this lands in A. Okay? And you repeat until you can't do it anymore. And why is this slow? Well, it's simply because this is very large. Okay, this quotient, like if you think as B, for instance, if you think that B is Z to the D, like it will be, for instance, in number of fields, then the number of elements here is P to the D. It's exponential in D. Okay? So that's why this is not a good algorithms to compute the saturation. It's a useful notion, but you have to apply it in a context where you can do better than this. So why is this important for our particular problem of computing the ring of integers? Well, okay, so we start with this order, and we are reduced to two steps. We want to find the p's that divide this index, the part that is missing. And, well, here is one overset of that, which is the set of prime factors of the discriminant, because, well, remember, this discriminant is just the discriminant of the ring of integers times the square of this. So we have access at least to the prime divisor of this. The problem being that factorization is slow, but it gives us these p's. And then for each of the p that we found here, we want to compute the p saturation of O inside of the ring of integers. And in this particular context, it has another name. We call this a p maximal order containing O. Okay, but it's the same definition, but just in this context we call it that. Or I guess, well, maybe in the group context, the p saturation was just a group. Here it turns out that the p saturation is not just a group, it's actually also a ring. Okay. And this we're going to discuss in a bit more detail, but we can do this in polynomial time for a given p. So in general, in the worst possible case, the bottleneck of this algorithm is just to factor the discriminant. Okay? On the other hand, for special classes of number fields, it may be that this discriminant is very easy to factor. There can be special reasons for it. And in this case, you can do everything in polynomial time. Also, there are contexts where you don't have to know the full ring of integers. It may be enough for what you want to do to just know a p maximal order at certain specific p. And then also you can do it quickly, and you should avoid factorization. And again, this is a bit of a frustrating problem because we're reduced to factoring the discriminant, but it doesn't look like it's completely necessary. In fact, you can prove the following. The problem of computing the ring of integers of arbitrary number fields is equivalent to the problem of finding the largest square free factor of a given integer. And this looks like it could be easier than complete factorization, but we have no idea how to do it faster. So, yeah. So this is for the factorization part, and now we will focus on this part, computing a p-maximal order. Okay, so there are two main algorithms to compute p-maximal orders. They have names. I don't know where they come from, but I'm giving you the names just so that if you see those names, you know what they mean. So the first one is called round 2, and the second one is called round 4. I have no idea whether there's a round 1 or round 3. The first one is purely based on linear algebra. And in particular, it has polynomial time complexity. It's a medium speed algorithm. So I'm going to tell you a bit more about this one. The second one, round 4, it's based on polynomial operation. So this is, again, an instance of we want to do polynomial operations because they are faster than matrix operations. And in practice, it's really much faster. However, we don't know how to prove that it actually terminates in polynomial time. So in principle, you could find absolutely horrible examples where it would be slower. So this is the one that's implemented in actual computer algebra systems. Usually, that's the one that they use. But I will describe this one, which is slightly simpler, and we can, in fact, prove something about it. Okay, so round 2, how does it work? So it uses the following theorem. You take your order O, and you consider the set of elements of O such that modulo P, they become nilpotent. So if you think a little bit about it, you can see that this is an ideal. Because, well, modulo P, if you have a nilpotent element, you multiply it by anything, you raise it to a power, you still get 0 for large enough power. And that's also true for sums by the binomial expansion. Okay? So this is, so mod P, you get an ideal, and when you lift it, you still get an ideal. And from this ideal, you can construct O prime, which is the multiplier ring of this ideal. That is the set of elements in the whole field, maybe not in O, such that when you multiply on the left on this, you still end up in there. So this is the largest ring for which this, in which this will generate an ideal. That's the way to formulate it. And you have the following theorem. So O prime here is always an order containing O, because this was an ideal, so definitely this relation is satisfied by elements of O. And O equals O prime if and only if O is p-maximal. So if you take O, you compute this ideal, you compute this O prime. If it's the same, then you stop. If it's not the same, you found a bigger one, so you can do it again. Now, the problem is the way I define this ideal, it's not clear at all how you would compute this, like the set of nilpotent elements. Being nilpotent, it's not a linear relation, it's a polynomial equation. It's like you raise it to some power, you get 0. So you have to rewrite this definition in a way that you can compute efficiently. And how you do this? Well, okay, I'm going to just give you the simplest case where P is larger than the dimension. That's just for simplicity. There are variants that work even for small p. Then an element of this, well, in fact, it works for any finite dimensional algebra over Fp. It's nilpotent if and only if the trace of A times x is 0 for all x in A. So if you think a little bit about it, why is that? Well, if you take, if A is nilpotent, then A times x is nilpotent for every x, and nilpotent matrices have trace 0. So definitely you'll have this trace 0. And on the other hand, if you have this relation in particular, all powers of A will have trace 0. And since the characteristic is large enough, from the traces of the powers of A, you can recover the characteristic polynomial. And what this tells you is that if all the traces of the powers are 0, the characteristic polynomial is just a power of x. That's exactly saying that the element is nilpotent. Okay? So we have this reformulation where this was nonlinear. We turned it to something linear. Okay? And so all of these can be computed by solving linear systems. You need to think a little bit more precisely about it to see that this is all linear algebra. But that's how you do this computation. And and just one thing, so when you increase this order, you divide the discriminant by p, so you can do it only a small number of times log of the discriminant. Okay, so I'm now going to describe a little bit about ideal arithmetic. So this is not, strictly speaking, one of the main problems that I had mentioned, but it's still quite important. And in fact, you, of course, need it to be able to compute class groups. So let's talk about algorithms for ideals. Okay, so a few things about ideals in rings of integers. First, we don't just consider ideals of the ring of integers, but more generally fractional ideals. So this is just a non-zero ideal of f with a denominator, okay, an integral denominator. And the basic results are that fractional ideals are invertible in the sense that there's another fractional ideal such that when you take the product meaning ideal generated by all products, then you get ZF. So that's going to be the neutral element of the group of fractional ideals of your field. You have a notion of norm on ideals. For actual ideals, it's just the size of the quotient, and you extend that multiplicatively to fractional ideals. And this is also compatible with norm of elements for ideals that are generated by a single element. You have unique factorization of ideals into products of prime ideals. In fact, well, all of this actually is true in Dedekind domains in general. And prime ideals always appear in the factorization of some prime number, namely the prime number that generates the intersection of the prime ideal with z. So if P is a prime ideal, intersection with Z is still prime, and prime ideals of Z, because, well, Z is a PID, they are generated by prime numbers. Okay, so all prime ideals appear in one of those factorizations. Okay, so before talking about what we do with ideals, we should talk about how we represent them. So there's two main options. We could represent them by the matrix of a basis of the ideal, basis over Z, simply because, well, they have, they are finitely generated over Z, so we can represent them by a basis. So that's one representation. The other option is using the theorem that tells you that every ideal can be generated by just two elements over the ring of integers. So here you need to be careful. This is not a basis over ZF. It's just a set of two generators. Okay. Both representations have their advantages. This one is a bit less compact than that one, but just for simplicity, I will stay with the first one implicitly when I describe algorithms for ideals. Okay. So the most interesting problem for just basic operations with ideals is the factorization problem. So we are given an ideal in the ring of integers of f. I mean, I'm just considering regular ideals rather than fractional here because you easily reduce fractional ones to actual ideals. And so the first thing you can notice is that it's at least as hard as factoring integers. You can just, if you know how to factor ideals, then definitely you know how to factor integers. So in particular, we should allow ourselves to factor some integers. And so we are going to divide factorization into 3 steps. First, factoring the norm of A. Why is that? Well, because the norm is multiplicative, that will give you a first information about the factorization of A. And in particular, it's going to give you the primes, the prime numbers above which the prime ideals that divide A are lying. So you factor completely the norm and you consider all the prime divisors. And then for each of these prime divisors, you have to find all the prime ideals of the field that appear in the factorization of P in here. So now what we're going to see is that this can be done in polynomial time. And once you've done that, then you have a set of candidate primes that could appear in the factorization of A. And for each of these, you should compute the exponent of P in this factorization. That's what we call the valuation of P in A. And as we'll see, this can also be done in polynomial time. So again, the theoretical bottleneck is factorization of integers. Because this we don't know how to do in polynomial time. But again, it depends a lot on your situation, depending how your ideal appeared. Maybe the norm is actually easy to factor, and then everything can be done in polynomial time. Okay, so let's see. So this first step, I'm not going to comment more. I'm going to talk about how to perform the next 2 steps. So how do we decompose primes into products of prime ideals? So I'm just going to describe a special case that gives the main ID. Well, so think about the factorization of P. So we're going to write it as a product of primes with some exponents. These exponents actually are 1 for almost every P, and they can only be different from 1 if P divides the discriminant of the field. These are the ramification indices. And so the way we're going to factor the ideal is by thinking of the quotient ring of the ZF modulo P. And if you have this factorization, well, by Chinese remainder theorem, this is isomorphic to a product of rings. And actually, what we're going to see is that we can go back from this ring decomposition to the ideal decomposition. Okay, so for simplicity, we'll assume that P doesn't divide the discriminant of Z alpha. In this case, we can look at at the defining polynomial P modulo the prime number P. This is going to be square free because we assume that P doesn't divide the discriminant. And so we can factor it as a polynomial over a finite field. We get a certain factorization. And now if you rewrite Z alpha modulo P, well, this is the same as Zx modulo the prime number P and the defining polynomial P. And then you can switch the quotient. You get Fpx modulo the defining polynomial modulo P. And because of this factorization, you get this product of rings. So this, which is in fact closely related to that here, I mean, this is actually P maximal, that's the point here, gets factored as this product of rings. And in fact, because the PIs are irreducible, all of these are fields. Okay, so this is actually the finest decomposition that you can get for this ring. And from this, you obtain that the prime ideals lying above P are exactly the PIs generated by the prime P, and these polynomials evaluated at alpha. This is just the pullback of the ideal of things that are 0 in the corresponding factor here, okay, which is an ideal of this ring. And for free, we get the residue field at the same time. It's just fp of x modulo this irreducible polynomial. So in particular, you know the residue degree, which is the degree of this finite field over fp, and you can compute in it, and you can naturally reduce elements of the ring of integers down to this finite field. Okay, now we know how to find the prime ideals that divide your prime number. And so we want to find the actual exponent that appears. And this is actually relatively simple. We can simply reduce the whole basis of A or a set of generators if you have generators modulo P, because now we know how to obtain the residue field of P. And we check if that's 0 or not. That will tell us if P divides A, so if there's a non-trivial exponent for P in A. And if that's the case, we divide by P. So dividing by P is, again, it's just a linear algebra operation. You can actually do better if you pre-compute some element with denominator at most P that has valuation -1 at the prime you're interested in, and 0 at all the other ones above P. And the reason for that is that when you multiply by Z an ideal, you will see denominators appearing if and only if you multiply by a power that is larger than the valuation with which P actually appears in the ideal. You look at the valuation of, maybe I should write it, of Z to some K times A. And this is just going to be VP of A minus K. And so for various values of K, at some point this will become negative, and that's where you're going to have denominators. So you can detect when K is actually equal to this, which is what you want. And this, so pre-computing this element can be done just by the same decomposition of prime that we just saw. So this gives the complete factorization of ideals. And okay, that's where I wanted to stop for ideal arithmetic. Maybe, is it a good time to make a break? So now we will talk about our second main problem in algebraic number theory, which is to compute Galois groups. So I will first give you a reminder or introduction to Galois theory. So a number field is called Galois if the following equivalent properties hold. So f is generated by the set of all roots of a polynomial in Q of x. So not just by a single root, but all the roots. Equivalently, f contains all roots of its defining polynomial. So you have a defining polynomial, which means that by definition, f contains one root of that p. And we ask that, in fact, f contains all the roots of p, factors as a product of linear factors. And equivalently, it has as many automorphisms as its degree. And as we saw, I mean, automorphisms are just given by other roots of the defining polynomial. It's a special case of the embeddings or isomorphisms of number fields that we saw earlier. So in this case, we give a different name to this Galois group. We call it to the automorphism group, we call it its Galois group. And there is a one-to-one inclusion reversing correspondence between subfields of F and subgroups of the Galois group. So this is the first interest of Galois theory. It converts this problem of finding subfields, which can be difficult a priori, to a problem of subgroups of a certain finite group, which is hopefully more algebraic, more tractable. And so that's for f that is Galois, but when f is not Galois, it automatically has a smallest field containing it, which is Galois, called its Galway closure, and that's simply the field generated by the set of all roots of the defining polynomial of f. So maybe f was missing some, p was missing some of its roots inside of f. If you join these roots, you get the Galway closure. And one other important properties of Galois fields is the presence of Frobenius elements in the Galois group. So this is an interaction between the Galois theory and the arithmetic of the field. Like what I said in the previous slide, this is more general for fields. But if you add arithmetic, you have an interaction with the Galois theory in the form of Frobenius elements. So we assume here that f is Galois, and we take a prime that is unramified. So in the decomposition, all the exponents are 1. And in this case, there exists a Frobenius element that's an element of the Galois group that is characterized by the following properties. Well, if you apply it to the ideal P, it's stable. You just get the same prime. So because it is stable, it actually acts on the residue field of P, and so it's going to be an automorphism of the residue field of P, and you ask that it's exactly the Frobenius automorphism of the residue field. And it has order equal to exactly the degree of the residue field. So in other words, the group generated by the Frobenius element is isomorphic to the Galois group of the residue field. Now, when you vary the Frobenius element over all primes that appear in the decomposition of a given prime number, they're all conjugate and they form a full conjugacy class. And so we'll have this notation from sub p, where p is the prime number for this conjugacy class. And so one example of something that Frobenius elements give you, if you look at the Frobenius element in the Galois group of the Galois closure of f. So now, so you have f, which doesn't have all the roots of the defining polynomial, and f tilde, the Galois closure, has all the roots. And so in particular, elements of this Galois group, they are automorphism of this larger field, which has all the roots. And so it permutes these roots. So you can think of Frob P as being a permutation of the roots of P. And if you look at the cycle type, I mean the orbits of the action of these Frobenius elements on the set of roots, that's exactly the same as the factorization type of P. So there's as many orbits as the number of prime ideals that divide P, and the length of the cycles are exactly the residue degrees. And that's really inside of F in the field that is not Galois. So these Frobenius elements, they tell you something about the field even if it's not Galois. Okay, the bottom one. So the main tasks are going to be compute the Galois group. It's a finite group, we want to compute it. Compute this Galois correspondence between subgroups and subfields, and compute Frobenius elements that are going to be the main ones for today. So really, there are two actual different problems. You could be given as input f that is Galois already from the start. And then the question is to compute the Galois group, which is the same as the automorphism group. And the other possible problem would be you're given f that is not necessarily Galois. You consider its Galois closure. It has a Galois group. You want to compute it as a subgroup of the permutation group over the roots of the polynomial. And why are these two very different problems? Well, if you want to pass from this to that, you have to actually compute the Galois closure itself, but it can have enormous degree. When you join the roots of the initial polynomial, the degree, which was d, could grow as large as factorial d. Okay, so this is one instance of what I mentioned also in the first lecture. You can have very different type of inputs for a given problem, I mean mathematical problem, but then because the input is so different, it's not actually the same problem and you won't have the same complexities. Okay? So in particular, for instance, just in terms of the size of the group that you want to output, here, because f was Galois of degree d, this group has size at most d. Okay? Whereas here, if f has degree d, this group can be a lot of different subgroups of the symmetric group, so it can have size at up to d factorial. Okay, so these are very different problems. So I will tell you a little bit about what you can do in these two cases. Okay, well, maybe first how you can relate the two is by computing the Galway closure. So how do you compute the Galway closure? You need to adjoin roots until you found the Galway closure. You start with the field that you had, and at every step, you factor the defining polynomial over the current field that you have. If you find a nonlinear factor, it means you can do a non-trivial extension. So you do that extension and you repeat. And so every step is polynomial time. This is just, well, we said a resultant to get the extension and a factorization of a polynomial over a number field. We said this is also polynomial time. But the size of everything that you consider grows so fast that the complete algorithm is not at all polynomial time. Okay? On the other hand, it's polynomial time with respect to the size of the output. Okay? Not of the input. Right, so this is the relation between the two. Okay, so first, I will consider the first problem where you assume that f is actually Galois. So here, computing the Galois group and the automorphism group is the same problem. So in general, you can compute the automorphism group, as we said, just by finding the roots of the defining polynomial. So it's just a polynomial factorization problem. We have a polynomial time algorithm for this. And this works for the automorphism group regardless of whether f is Galois or not. You can always do this. So it's polynomial time. It's a medium speed algorithm, but you can actually do faster than this generic method. So there is a combinatorial algorithm that exploits, I mean, I'm not going to go into details, but it exploits the existence of Frobenius elements. It tries to find one that generates a normal subgroup, compute the corresponding subfield, which is also going to be Galois, recursively compute in the smaller field, and then tries to go back. And so this works only for a special kind of Galois groups called supersolvable. Doesn't matter what it actually is. It's a group theory notion. And it's quite fast in practice, but it can be exponential in the worst case. So there are cases where it's going to be very fast. There are cases where it's going to be very slow. If you specialize even more, so here we specialize to supersolvable. If you specialize even more the type of Galois groups, so either abelian or nilpotent. So nilpotent means it's a direct product of its p silo for various p. It's a product of direct product of p groups. Then you have other polynomial type algorithms that also work with this kind of recursive structure, but they're actual polynomial time and they are much faster than the generic one that I mentioned. Okay, for the other operations, well, computing subfields, the subfield corresponding to a subgroup, this is actually quite simple in this form. You can simply generate it by taking the trace of a certain element in F. And you can compute this trace by reconstruction. You just compute the roots of your polynomial. You apply the permutations. You construct over C or some other reconstruction, the polynomial that vanishes exactly at the corresponding elements, and you identify it as a polynomial over Z. And this is polynomial time. Similarly, in this context, computing Frobenius elements is basically just applying the definition. You just try every element of the Galois group and you test it for the definition of Frobenius elements. Does it have the correct order? The order should be the degree of the residue field. You check if it stabilizes the P that you're interested in, and you test if it induces the Frobenius automorphism. That's all. And that's polynomial time. Okay, so that was for the first type of problem where the field we are actually starting with is Galois. So now we're going to do the, well, in fact, harder one where we start with a field that is not Galois, and we want to compute the Galois group of the Galois closure without actually computing the Galois closure because it's too large. Okay, so here is the general strategy to do this. We're going to maintain a subgroup of the symmetric group satisfying the property that the Galois group is actually contained in G. And we will try to make it smaller and smaller until it's actually exactly the correct Galois group. So we start with the symmetric group because we know the Galois group is contained, it's a subgroup of the symmetric group. And we'll repeat the following operation. Compute the maximal proper subgroups of G. So, we're in a finite group, so there's only finitely many subgroups that are, maximal, so there's no intermediate one. And for each of these, we test if the Galois group is contained in that, and we go down like this. So, step 4, I'm not going to tell you more about it. This is quite non-trivial computational group theory. And in fact, there's no known polynomial time algorithm to do that. But there's a variety of methods and tricks that make it fast in many cases, but yeah, I'm not going to say more about it. I'm going to tell you a bit more about how you test this. Do you have a containment like this? So this uses the method of resolvence. So we start with the assumption that the Galois group is contained in a certain G. And we have another H. We want to test if the Galois group is actually contained in H. So for that, we're going to need a multivariate polynomial F. So if you have a multivariate polynomial F like this, you can act on it by permutations, by permuting the variables. Okay? So when you do this, it will have a certain stabilizer. Certain permutations are going to stabilize it and others won't. Oh, I should have said that H should be actually a subgroup of G, sorry. And so here we assume that H is exactly the stabilizer of F. So part of the algorithm will be to actually construct F that have a given H as the stabilizer. But here we assume that we have it. Then we can define the following resolvent polynomial, which is the product over cosets of H in G of X minus evaluation of F at the roots of P permuted by sigma. So from the assumptions, it turns out that these coefficients actually lie in an extension of F a priori. It actually lies in Zx. It's a polynomial with integer coefficients. And just from the definition, you can actually compute it again by reconstruction. You can do these evaluations with, for instance, complex roots at sufficient precision, compute this product, and if you have enough precision, you can identify everything as integers. And what is the point of this construction? Well, this resolvent polynomial might not be square-free when you're in bad cases, but you can do extra work to make sure it is. If it is, then it has a root in Z if and only if the Galois group is conjugate to a subgroup of H. And so you can do this whole computation by reconstruction and then factorization to get the roots of the polynomial. And so these are fast operations in terms of the size of this resolvent. And this is the whole problem. The bottleneck here is to find f's that construct a polynomial here that is not too large. And this is also difficult and not known to be doable in polynomial time. But this general strategy works in a number of cases. People actually add a lot of tricks to make things faster, like to refine this general strategy so that it actually works in practical instances. Okay, so for subfields, I won't say much about it, but you can use resolvents also to produce the subfields corresponding to a subgroup. I'm not going to say more about it. And Frobenius elements use variants of this resolvent strategy. So it's, again, something that works by reconstruction. So the way it works is, so Frobenius elements, there are conjugacy classes in the Galois group. So what you're going to do is, for each conjugacy class, you're going to construct a polynomial, and evaluating those polynomials at certain well-chosen elements will tell you in which conjugacy class the Frobenius element lies. So you take a conjugacy class, you construct a certain polynomial. Okay, the precise shape doesn't matter that much for now. It's another type of resolvent, basically. And the theorem tells you that the Frobenius element is in a conjugacy class if and only if, when you evaluate this at a certain trace modulo p, you get 0. And the point is just that this, if sigma is actually the Frobenius element, the permutation of the alphas gets replaced by the Frobenius element, so like the Frobenius automorphism of the residue field, so just raising to the power p, and this sum then becomes a trace, so you get exactly this.
Why for almost all?
Why for almost all? There are p's, well, first, there are p's for which the Frobenius element is not defined, and also so there's extra work that you need to do to make sure that these resolvents are co-prime to each other. What could be bad is that they have common factors. And even if you do that, there could be some p's for which these polynomials are not co-prime mod p. In which case, when you evaluate this, you could have a root for several of these gamma c's. And that's what goes bad. So you know then that the Frobenius is in one of these conjugacy classes, but you don't know which one. Okay, so that's, oh yeah, sorry, I wanted to make an extra remark about, so this is not quite Galois theory, but related. Sometimes you just want the subfield of F, which is not necessarily Galois, but you don't need to compute the actual Galois group for this. So one first problem is that the number of subfields of F doesn't need to be polynomial. Actually, if you think about Q adjoin a lot of square roots of integers, and you look at what the subfields of these can be, they correspond to vector subspaces of F2 to some power, and the number of these can be like 2 to the n squared. So it can be larger than polynomial. So there can be lots of subfields. So there's a notion of generating subfields which are a small number of subfields such that all the other ones can be obtained by intersecting those. So this is a way of, in some sense, computing all subfields without actually writing them all down. Okay? And it uses subfields of a special form, the set of elements, such that two morphisms to another field actually agree on this element. It's quite easy to see that this is a subfield, and this is the type of fields that you want to consider. And this is, again, something that you can obtain from polynomial factorization, so polynomial time. Okay, so finally, I want to give you an overview of what we can do to compute class groups and units of number fields. So recall that a fractional ideal is principal if it's generated by just one element. And the class group is the quotient of the group of fractional ideals by the subgroup of principal ideals. That's a finite abelian group. And on the other hand, the unit group of the ring of integers, it's a finitely generated abelian group of rank R1 plus R2 minus 1, where this is the signature of F, meaning R1 is the number of real embeddings of F and R2 the number of pairs of conjugate complex embeddings. So these are the two main objects we want to compute. So what we are going to see is that actually we usually compute these two. I mean, even though they don't look like they're so related, we essentially always compute them at the same time. So here are the specific problems we want to solve. We want to compute the structure of these as abelian groups. More precisely, we would like to know generators of these groups according to the structure that we computed. Given an element of the class group, so given by an ideal representing the class, or a unit as an element of the field, we want to be able to write it as a product of the generators. That's what we would call a discrete logarithm problem. Again, well, in a slightly generalized sense here. And given a principal ideal, we would like to be able to compute a generator of it. So knowing whether it's principal, that's the same as this problem, because we take A, we want to write it as a product of the generators, and, well, okay, maybe you need something like a basis to identify that it's actually 0 in the class group, and then you want to compute a generator for it. So the reason that we usually do both at the same time is basically because we reduce everything to computations with S units. So S units is a slight generalization of the notion of units. You take a set of prime ideals of your field, and then the group of S units is by definition elements whose that generate an ideal in which only the primes in S appear in the factorization. Okay, so another way to say it is the elements such that the valuation is 0 for all P that is not in S. Yeah, that's the same. And a slight generalization of the unit group theorem is that this is a finitely generated group again with rank that increases compared to the units by just the size of S. Now, why is this relevant to, well, it's maybe quite clear that it's relevant to unit groups because it's bigger, but for class group, well, if S generates the class group, then you can consider the map going from S units to one copy of Z for each element of S, given by take an element and send it to the vector of its valuations. Okay, so that's a well-defined map. And because S generates the class group is just prime ideals supported at S modulo ideals among those that are principal. And that's the same as the co-kernel of this map. So like this modulo the image of that. And on the other hand, if you have an S unit, when is it an actual unit? That's exactly when it generates the trivial ideal. So when all the exponents in the factorization of the ideal it generates are 0. So it's exactly the kernel of this map. So you can pack together the two problems by looking at S units. And well, the other problems also essentially reduce to this. For instance, if you have an ideal that factors completely over the primes of S, and it's actually principal, then you can find the generator among S units. So again, you reduce to computations with S units. So this is the important notion that is used for these algorithms. Okay, so first I'll do one simple case where when you consider the unit group and you just want the structure, well, Dirichlet's theorem on the ring tells you almost everything. The only thing that you don't know is the torsion part. You have to determine how many roots of unities there are in your field. But in fact, this is somewhat easy because if you have a root of unity of order m inside of your field, then in particular you have an embedding of the field generated by that root of unity inside of F. And so the cyclotomic field of the corresponding to M, and therefore the degree of that field, which is called phi of M, the Euler-Tauschen function, has to divide d, the degree of F. And so you can deduce the finitely many possible m's just from this relation. And they're all small. And then for each fixed m, you can simply factor the cyclotomic polynomial over F to see if it has a root. And this way you'll determine which roots of unity are actually contained in F. So this is polynomial time. So this is the only part that is really easy in this computation. Okay, so before talking about the algorithms, I just want to mention one dependence of the algorithms, namely the Riemann hypothesis. So as you may know, this product over primes, prime product of 1 minus p to the s to the minus 1 for s, sufficiently large, real part complex number, this converges, and you can continue it to meromorphic function on C. And there's a very, very big conjecture about this function, which is that all the zeros of F have real part at most 1/2. And there's a generalization of this conjecture to other L functions related, for instance, to the field that you're going to look at. And we call this the generalized Riemann hypothesis. That's a very hard conjecture that no one knows how to prove, but it's going to play a role in the correctness and the running time of the algorithms, so you have to be aware of that. So here is the situation. Assuming GRH, we know how to solve all of these problems in sub-exponential time, so slow algorithms, but at least not exponential. So precisely, there's a certain dependence on the degree, so maybe the only thing to look at is here the exponent 2/3 here, and some dependence on the discriminant where the exponent is 1/2. So what we can prove here is actually that the dependence is slightly better in the discriminant than in the degree. So this algorithm, not only we can only prove this running time under GRH, but it's even worse. If you don't assume GRH, we don't even know that the output is correct. So unconditionally, the output of this algorithm could be complete garbage, have nothing to do with the correct output. Unconditionally, we only know exponential algorithms. So for the full computation, discriminant to the 1/2, essentially. And if you only care about the unit group, you can do slightly better, exponent 1/4, but still exponential. And in practice, what you do is you don't really apply these unconditional algorithms, even if you want an unconditional output. You apply this one, and then you run a certification algorithm that does extra work to remove the dependence on GRH. Okay, so that's for the theory. In practice, the behavior of this algorithm is actually quite difficult to understand. And in particular, we don't really see the fact that it's harder in terms of the degree than the discriminant. In practice, it actually looks like for fixed discriminant, if you increase the degree, it becomes easier, which we absolutely don't know how to explain. So for instance, you can expect to be able to go up to degree about 100 for general fields. After that, you probably won't be able to do the computation. And then the discriminants will be maybe, this is an order of magnitude 10 to the 200, for instance. On the other hand, for small degrees, you will be stuck a bit earlier in the discriminant. And I would just want to finish on algorithms for special cases where you can do better than these slow running times. For instance, fields that have a very special structure, such as cyclotomic fields, will have specialized algorithms that work better on these. So I'm not going to say much, but for a cyclotomic field, you can extract partial information, but for very large ones. And there are also algorithms that exploit the special structure of the automorphism group. And depending on how special this one is, you can do much larger. For instance, you can reach degrees up to almost 2,000 and large discriminant as well, under some very special conditions on the automorphism group. And that's where I will end my lecture. Thank you, and I'll take more questions if you have.